Swayam Prabha. Digital India. Educated India.
So this example shows you a very practical problem, as you can see on the screen. So you have a sort of a cantilever beam, and which is subjected to some moments and torques and axial load and so on. Now, as a result of all of these different kind of forces and the moments and the couples which are acting at some point within the beam, this is the state of stress. So you see here also the sides of the element are perpendicular to the longitudinal axis and the top of the elements are parallel. And from the things which you have learned until now, for example, you see as a result of this torque T, you will have that element in pure shear. As a result of the moment, you will have the normal stresses. As a result of P also, you will have the normal stresses. So this is the a combined state of stress out of these different forces. So it's a very practical example, because in structures in reality you have all these sorts of forces which are acting over there. Now, because of this, what you are shown is the state of stress. So if you take a look at the state of stress over here, you see your sigma x is minus 12 ksi. So we may want to make a note of that. So equals to minus 12 ksi, that is there because it's compressive. Your sigma y is 0, you have no stress in the vertical direction, and you have the tau xy. So tau xy, if this is your positive x and this is your positive y, tau xy generates on the positive face but points towards the negative direction. So tau xy is minus 6 ksi. So this is ksi means kilopounds per square inch. So tau xy equals to minus 6 ASI over there, right? Now, for this, what the problem asks you is to find that what are the principal stresses at the same point is. At the same point, if you take a different, instead of taking the element with the faces perpendicular and parallel, if you take an inclined plane, so you're trying to find that for these generalized loading case, for another plane, where does the stresses peak up, where the normal stresses become maximum and minimum. So let's go ahead and do that. So as you remember that for the Morse circle, and I will come to the circle in a minute, for the Morse circle, the center of the circle is at sigma average comma 0. So the center of the circle C is usually the ordinate is sigma average and 0. So here the sigma average is sigma x plus sigma y by 2. So this is minus 12 plus 0. So it becomes equals to minus 6 ksi. So you see that the center itself is in a negative sigma. So if you draw the Morse circle, these are the axis which is there. Now always remember that my axis towards the right I have the positive sigma, and towards the bottom I have the positive tau. So this is our convention, and as I said, different books have different convention, and this convention we are following is the easiest one to have a one-to-one mapping from the real plane to the Morse plane over here. Okay, so now we have marked the centroid of the circle, or the center of the circle C, where we know the ordinate is sigma average comma 0. So the distance from the origin, this is the origin of your coordinate system, from here to C is this value of minus 6. So let's maybe go ahead and mark that one as well. So this distance that we are seeing over here, that from C to this guy over here, so this is a value of minus 6 that you are seeing over here. So the point C is sigma average comma 0. All right, so now the first point is that after marking the C, that we have to find we have to mark the point A. So the A is what? A is the original state of stress that is there over here. So remember, for A, the point A has the ordinate sigma x and tau xy. So the sigma x is minus 12 and the tau xy is minus 6. So minus 12 means of course to the left of this on the origin, and the minus 6 means it should be up because tau is positive downward. So maybe at some point over here I have the point D. So let's go ahead and mark the point A also in this figure. So maybe this is my point A, which is there, and the ordinate of A is minus 12, that is for the sigma, and minus 6, that is there. Okay, so now my next job is to join C and A and find the radius of the circle that is there. So let me go ahead and join that. So I have joined the point C and A, and this is my the radius R. So this is R, and the value of R you can easily compute using this triangle that we have over here. So for this triangle, I know that this height that you see over here, this particular height is 6, and this distance is going to be minus so this minus 12 that you see, it is from here to here. This is the total distance 12, and up to the centroid is 6, so this is going to be 6. So if you take a look at the magnitude, so what we can write, that our r is going to be square root of this distance square, that distance is 6 square, plus this distance is also 6, because the total from here to here is 12. So that brings out your r as 8.49. Right? So this is our radius. This is just the magnitude of the radius, that is 8.49. So this is just be calculated equals to 8.49. So now we have everything set. We have the circle which is drawn, we have located the centroid and also the initial point A. Now the question is that to determine the principal stresses. Now remember, the principal stresses are always the extreme right and the extreme left. So here the extreme right is this point over here. Now here I have pre-drawn the circle after initially calculating. This whole circle may be in the negative plane also. So let's see what are the points that we get. So this point, the maximum I indicate by sigma 1 and the minimum by sigma 2. And now you see, compared to plugging in the equations, it's just so easy to calculate these different stresses that you have over here. For example, what would be the value for this guy sigma 1 over here? I know that this particular distance that is, so it will be the extreme ends over here. So this is my centroid over here. So this C, and I have to take this radius, and I have calculated the radius already, and I have to take this account of this radius to calculate sigma 2. So let's calculate this sigma 1 over here. So since the radius is 8.49, the value of the sigma 1 that you will get, the distance of sigma 1, remember the value of sigma 1 is always the distance. So any point is the distance from the origin that you take. So the distance from here, let me mark that, from here to here, this is what you're trying to find. So that is going to be, your radius is 8.49, so minus 6 will be your sigma 1, and similarly your sigma 2 in this particular case will be minus 6 minus 8.49. So let's go ahead and write that. So these are the two extremums of the principal stresses, which are the sigma 1 comes as just a small positive 2.49, and sigma 2 is minus 14.5. So we have found the principal stresses. Now the question is to find the directions, because along with the stresses we have to find along which element it is, or along the which angle of rotation it is also acting. So the easiest way to do that is, so from CA, remember, angle of 2 theta rotation in the mode plane corresponds to angle of theta rotation in the original plane. So from your CA, if I have to reach this particular sigma 2, I can go this anti-clockwise manner over here, and this angle which will correspond to your 2 theta P2. Why? Because 2 theta P2 corresponds to sigma 2 over here. So let's go ahead and calculate that. The easiest way to calculate, we take the tangent of this is this height, that is the 6 divided by this particular dimension, this particular length that we have over here. So that is also 6. We know that one over here. So let's go ahead and calculate. So 2 theta P2 comes out as 45 degrees. So that means in the original plane it will be 22.5. Now it is important here excuse me, it is important here to note that, see, the sense of rotation is also preserved. So here the rotation is anti-clockwise. So in the original plane also the rotation must be anti-clockwise. So at an anti-clockwise angle, so the face which bears, so the easiest way to think of it is that the face of the element which bears this load of sigma 2, that is minus 14.5 ksi, must be at an angle of 22.5 degrees over here. So let's go ahead and draw that one. Draw the rotated element. So this is my rotated element that I have now, where this was my original x-axis and now it has undergone a rotation of 22.5 degrees. This is the outward normal. So an anti-clockwise 22.5, and on this face the stress which is acting is theta is sigma 2 over here. So see, it's so easy that now with the Mohr circle you can directly correlate which angle corresponds to which stress, which was quite difficult in the approach when we were just using the equations, because we have to plug it back to the basic equations and find out that which stress corresponds to that angle. So let's go ahead and mark the stresses. If you mark one of them, the rest are easy. So for theta P2, I have this sigma 2, which is minus 14.5. It is a compressive stress, and the other stress is tensile, that is 2.49. Of course, it has to act in the other faces. These are the tensile stresses that you have, 2.49 and 2.49. Now, you may be wondering, this is a natural question to have when you're looking at Mohr circle for the first time, that we did this 2 theta P2 and we got this one over here. Now you might be wondering that why did I not go from this line and do a clockwise rotation to sigma 1? You can do the same thing, and you can see that what it will give you. So if you calculate that, so suppose if you are calculating say this angle over here, right? Suppose this one is your 2 theta P1, which is equals to nothing but 180 degree minus 2 theta P2, so that is 135 degree, right? And so that means that this gives your theta P1, and the sensor rotation was clockwise over here, so that gives your theta P1 as 135 divided by 2, 67.5 degrees, right? So now you see that here the sense of rotation was clockwise, and a clockwise 67.5 degree. So if you have to mark this face over here where and remember this is for sigma 1. So you see here this face essentially is that. So this face essentially, if you mark again from the horizontal, from the horizontal, this face has rotated by this large angle of 67.5. So if you from here, if you mark this outward normal that is there, this angle is essentially 67.5 degrees, and because this one and this one makes a perfect right angle, because it's separated by 180 degrees, so in the real plane it must be separated by the 90 degrees over here. So it really doesn't matter which face you start with. Once you draw one of the faces, the other faces are automatically determined over there. Now another way, instead of going from here to here in a clockwise manner, you could have gone from from the origin CA, from this line, in an anti-clockwise manner to this sigma 1 over here. You could have done that as well, and that would have given you this angle. So it will be an anti-clockwise, a large rotation that you would have gotten. So that would have given you this whole angle over here. So it really doesn't matter which face you start with. We start with the closest one, and all the other ones gets automatically sorted out. So I hope this problem example was clear, and how easily we could calculate the principal stresses using the Mohr circle method. It's a fun method also to look at, rather than keeping on plugging the numbers in the equations and doing it in a mechanical manner. So this is a problem example we have seen previously also, where we had that bolt which was undergoing this failure, for which at the failure point, this was the state of the plane stress which you were having. Remember, sigma x was minus 20 because it's compressive, sigma y is a plus 90, and tau xy is a positive 60 that you have over here. So now we are asked to do the same problem, but now using Mohr circle, and you will see how easy it becomes to do this problem in using the Mohr circle. You don't have to plug it in different equations. You don't have to wonder that which theta corresponds to which sigma and so on. So let's go ahead and do this. So first I will draw the general shape of the Mohr circle and start marking the different points which are there. Now remember, one of the first things to start with is to find the central point, or the point C, the center of the Mohr circle, which is where the stresses are average, that is C, that sigma average equals to sigma x plus sigma y divided by 2. So let me go ahead and calculate that and draw the circle and come back. So this is the Mohr circle which I have drawn. Now here you see the positive sigma to the right and the positive tau to the below. And the reason why this has sort of spilled to the negative side over here, because you remember our reference point of sigma x prime when theta equals to 0, it corresponds to that -20. So that's the reason it has shifted a bit to the right. So let's first say, if this is my, remember the original state of stress, this one over here, if we just mark this as point A, where point A, your sigma x prime corresponds to -20 and tau xy corresponds to +60. So if we go ahead and mark that point also. So first let's mark the circle and then the point A. So I have drawn my Mohr circle, and a part of it is sort of spilled over to the negative sigma over here. The reason, because if your sigma x prime when it is theta is oriented at 0 degree, that is at point A, the first point which we try to find in the Mohr circle, it has a negative 20. So I have marked the C over here, where C is the center of the circle at a distance of 35 from the origin. So we have already found this one over here. Now let's first locate the point A. Remember, the point A corresponds to the state of stress where sigma x prime is equals to sigma x that you have over here, and tau x prime y prime equals to tau xy. Essentially theta is oriented at the 0 degree over here. So let's go ahead and mark the point A. So the A will have an ordinate of -20 and +60. So the point A, if we have to write over here, so A will have the ordinate of -20 and 60. So let's go ahead and mark this point A. So maybe it will be somewhere over here, say this particular point. This is my point A, right? So if this is my point A, that I get, which is at -20 and 60. So my next job is to find the radius of the circle. So I am going to join C with A to find the radius of the circle. So this is my R, my radius of the circle, and it is easy to calculate because you see from this triangle over here, I need to just find R that is there. So that will depend on what? That will depend upon this length, which I know already what it is. So since this is 35 and this is at a distance of -20, so this entire length from here to this point, this becomes equals to the physical, just the distance becomes 55, and here this vertical is the 60, the positive 60 that is over there. So if we just go ahead and find the radius R that is there, so we know that R is going to be square root of 35 plus 20 square plus 60 square. So if you calculate this one, what you will eventually get is 81.4. So the radius of the circle is 81.4. So R we have found out as 81.4. So now that I have located this one over here, now you see how easy it becomes to locate the principal stresses. So these are the two principal stresses which you have at the extreme right and the extreme left over here. So let's go ahead and mark that. So this one I'm going to call this is my sigma 1 and this is my sigma 2 over here. Now how do I calculate sigma 1? Very simple. I know from the distance from the origin to this point C is 35, and plus I have to add the radius over here. So sigma 1 simply becomes equals to similarly, your sigma 2 is nothing but this 81.4. So you will have this 35 minus 81.4. So that will be the remaining this chunk that you have over here. So that one becomes So I have found the maximum and the minimum stresses, which are the principal stresses, and for these cases remember the taus are equals to 0, that is there. Okay, so now the question is that how do I have to rotate, or where do I have to rotate? So now sigma 2 corresponds to the theta p2, remember. So how do I get from in the Mohr plane? So our rotation of 2 theta in the Mohr plane corresponds to theta in the original plane. So from here, if I have to go to sigma 2, I have to go the shortest way I can go this, I have to have a clockwise rotation over here. So let's just mark that. So this one, So this angle is nothing but your 2 theta P2 that you get over here. So this particular angle is 2 theta P2. Now if you calculate 2 theta P2, so the tangent of 2 theta P2 will be equal to what? The tan of 2 theta P2 will be this perpendicular divided by this particular base. So it is going to be the 20. This value was 60 over here. 60 divided by this one. This distance is 35 plus this 20, which is 55. So that is going to be. So if we just calculate that one, so we have our tan of 2 theta P2, remember, because twice the rotation in the mode plane, which corresponds to 1 unit of rotation in the original plane that is there. So that is going to be equals to 60, which is this vertical ordinate that you see over here, divided by this horizontal ordinate. 60 divided by 35 plus 20. Right? So if you calculate that, you will get the value of theta P2 that comes out as 23.74 degrees. And also note, the sense of rotation is also preserved. So the sense of rotation here is a clockwise sense of rotation that you have. So we might also want to write that. So it is clockwise. Right. So now that one of them is fixed over here, it is easy to draw your entire element. Now remember, if you instead of calculating this, if you calculate this one, the eventual element that you will get, the shape is going to remain the same. So let's just draw for this and I will explain a bit more over here. So you say here we have to do a clockwise rotation of 23.74 to get this sigma 2, which is minus 46.4. Okay, so let's first imagine that how we are going to do this. So how we are going to do this, I'm going to first explain and then maybe erase that line. So if this was my original starting point over here, right, I don't know whichever point that was, I am having to rotate that clockwise as 23.74. so if this was my original plane, then I have to rotate something like this, so that I am preserving this angle of 23.74 over here. And so once one of the sides is fixed, the other sides you can automatically mark. So let's go ahead and mark this one over here. Let me just quickly erase that and draw the rotated element that we have. So I have this 23.74, have a sense of a clockwise rotation, and here I know the stress is this one, minus 46.4. So once I know one of them, I know the other one is going to be the 116.4, and the other on the other faces will be equal and opposite. So let's go ahead and mark that. Right now you might be wondering that I started with this angle over here, why don't I calculate, I started with this angle over here, so why don't I calculate this one and try to find that what is the sigma 1 is going to be, and that is also going to be the same if you try to mark that one. Let me do that also for you. That so here, instead of calculating 2 theta P2, suppose I go from here to this one over here, where a sense of rotation is anti-clockwise. So in this space you have 2 theta P1, so that is going to be 180 degrees minus 2 theta P2. Now if you go and calculate that, so that will be let me just calculate that over here. So that will be 132.52 degrees. So it becomes equals to 132.52, right? So that means your theta P1, your theta P1 becomes equals to the half of that one, so that is 66.26. Right. So you are seeing that an anti-clockwise rotation of 66.26 will correspond to your sigma 1. So you see it is the same thing, but it is essentially the same thing. If you start with the this, if you look at this face over here, this face corresponding to your horizontal line, this face makes this anti-clockwise, this angle is 66 0.26 degrees, and the value is 116.4 that you have over here, 116.46. so it is essentially whichever you start with, once you draw one of the faces, the other faces get automatically fixed. So don't be bothered that why are we starting with this and why not this. You can start with this particular thing as well, right? Also, you may be wondering that, okay, instead of going in anti-clockwise from here to here, why don't I start from here and go to this particular angle? You can do that as well. That is also a clockwise rotation. Which face is going to give you? It is going to give you this particular face over here. So if you calculate this whole angle and if you divide by 2, that is going to be, so you see the sense of rotation here, if you are going from here to here, is clockwise. So here also, if you go and mark this particular face, so what you essentially get, this is the bigger clockwise rotation that you're going to get. So whichever face you go, eventually you will end up with the same diagram. You can try it out on your own and you can see that one as well. So anyway, so this diagram that you see, it is exactly identical to what we had derived previously, but now it's much easier to do because you do not have to, in the previous one, remember, we had to calculate the theta, then we had to plug it back to the basic equation to find out that which sigma it corresponds to. So here in the Morse circle, you can easily get which stresses corresponds to over here. So that takes care of your this first problem over here. So the next one is to compute the maximum in plane shear that we have over here. So the maximum in plane shear, so let me just erase some of these things and then come back to you to calculate the maximum in. So the points of the maximum in plane shear are the very top and the very bottom of the Morse circle that we have. So let's go ahead and mark that. So which are essentially these two points that we have over here. So let maybe write these as E and F, right? So to get the value, so here the value of the normal stress is equals to the average stress 35, and the value of the maximum shear, as you can easily tell, it is just going to be the radius, that is 81.4. so you see here also an advantage of Morse circle is that you do not have to separately calculate what is the tau xy maximum. It is equals to the radius of the circle that you have over here. Now if we go ahead and mark that line over. So from this, so this is the point of maximum shear, and the value we know is your 81.4. so let me go ahead and write the coordinate for that one. So the coordinate of that one is 35 and 81.4, right? And now to go from your point A, remember, is the original place that you have over here. To go from point A to the point F, how do I have to go? I have to go in an anti-clockwise manner. So let's just go ahead and mark that, and this angle is going to be 2 theta s. Right, so how do we calculate this angle 2 theta s? You can again use your properties of your trigonometry to calculate this angle 2 theta s, or simply the easiest thing is that remember that the principal plane and the shear plane are situated 45 degrees away in the original plane. So in the Moore plane it's 90 degrees away, and that is exactly what you see. You see this plane and this plane over here exactly 90 degrees away from each other. Now we know this 2 theta p1, so 90 degree minus 2 theta p1 will be 2 theta s. So and from that you can calculate the theta s. So I will just go and calculate that and write it out over here. You can come back later and check. So theta s comes out as 21.26 degrees, and you see the sense of rotation here. The sense of rotation is anti-clockwise. So in the original plane also, it is going to be anti-clockwise, and the angular rotation will be 21.26 degrees. So let's go ahead and mark the element that is there for the in plane maximum shear. It will rotate in an anti-clockwise manner. So this is the rotated element that is there, and let's mark the stresses in this one. So here this was my original horizontal, and now the outward normal for this points at 21.26 degrees, right? And here the value of the shear you see is positive, so it is going to be pointing in this direction. And once you have one of the shears done, the others automatically get fixed. And also in addition to this shear, we have the value of which is 81.4. You also have the normal stresses, that is equals to 35 that you have. This is this guy over here, 35. So let's mark that. Positive 35. That is tensile. So I hope that this problem example with the Mohr circle, it made your life much easier rather than having to remember and plug in into equations that is there. So first, as we did, was that first we located the point C, then the point A, the radius, and then it becomes very easy. We took a bit more time and elaborately explained this one. So it's actually very easy and very quick to figure out. So once you try to do a couple of problems on your own, you'll be able to draw the Mohr circle very quickly, and then you can mark the principal stresses and the maximum intense shear also very quickly. Until now, what we have studied is essentially the transformation of stresses. So you were given the set of stress at a particular location within a structure. We have looked at an aeroplane structure, a bolt which has failed, and so on. And we see that about a rotated set of directions, you get the maximum principal stresses and the maximum in-plane shear. Now you might be wondering that how is it of relevance to you? Well, it is. For example, if you are a civil engineer or a mechanical engineer, or you are working with structures in general, there can be different planes than what we are established to finding in terms of the stresses. So until now we have mostly the bending stresses and the shear stresses. All that we have found are for those planes which are either perpendicular to the longitudinal axis or parallel to the longitudinal axis. Are there different planes? And I am going to talk with respect to the beams that we are usually seeing, and we have already seen that sections in beams can be represented as these 2D plane stress elements that we have over here. So the question is that for beams, although we have studied that how the bending stresses evolve and how the shear stresses evolves, can there be planes about which the failure is more likely than the planes which we have studied? So that is the main focus of this particular topic of discussion that we have over here. Now, if we take a look at a beam in general, so this is a general beam with a loading that you have over here. And what I have done over here is a small chunk of the beam which we have separated. Now, if we take a look at this chunk, let's see that what we have learned until now. So if I go and separate out this chunk that you have over here. Now for this chunk, and if I draw it maybe in a slightly enlarged format. So these are the broken edges where I have separated out the section. Now here, what we have seen, how the bending stresses evolve, and say in this particular case, since you have a cantilever with a load, you have a overhang, not a cantilever, it's a simply supported beam with an overhang, and say because of this one, maybe there is a tension at the top and the compression at the bottom and so on. So let's just draw the stresses that we have over here. So if I represent the stresses for this beam, it is something like this over here, where, as so this is my neutral axis, and on this side also I will have a similar profile of stresses that we have over here. So if I'm saying the top is in tension, the stresses act like this, the bottom is in compression, and here also say the top is in tension and the bottom is in compression over here, right? So if we take a small element within the beam, so within the beam, say you take a small element anywhere here, so due to pure bending, this element is subjected to these kinds of stresses over here. And where do the stresses peak up? As you can see from the figure, the stresses becomes highest at the edges over here. So if you take this element at the top over here, for this element, you will have the maximum stresses as sigma m, right? So this is for bending. So this was for the bending case. Now in addition to the bending, we have also studied the shear, right? Shear, for that matter, that like if you take the cross section of the beam, so this is along the longitudinal axis. So this is still, if we have this is my y axis and this is my x axis over here. So this is again my y. In this diagram, I have simply separated this small chunk of the beam that I had over here. But suppose if I'm looking at a cross section of the beam, any cross section for that matter, suppose if you're looking at a cross section, so yeah, along that cross section, and say the beam has a prismatic cross section, so maybe the cross section looks say, let's just for the sake of discussion, maybe it's a rectangular cross section. So here what would be the axis? Here this will be y and this will be say z, right? Because you're looking at the cross section of the beam. So you have a x-axis, y-axis, and your z-axis may be pointing like this over here in a 3D kind of a sense, right? So now if you look at the cross section, what we have seen, the shear stresses, it starts with 0 stresses over here, and it has peak stresses over here. For the rectangular one, remember it is 1.5 times the one that you have at the very end, and then you have again the 0 stresses at the end, and you have a parabolic variation throughout. Now because of complementarity, of course you will have stresses in the longitudinal direction as well. For example, if I am say looking at this beam in a 3D, so along with this I will have these longitudinal stresses, and these longitudinal shear stresses, remember it acts about that x-axis that you have over here. So this is the x-axis, right? So that essentially means that if again I am looking at the this kind of a configuration, so because of these longitudinal stresses at the center of the beam over here, I am going to have shear, right? I will have shear stresses. Now see, the interesting thing is that, so here in this shear stress, this arrow which I drew is about this section. This is the vertical line over here, and this arrow which is here, which is about the longitudinal axis, about the x-axis. This is these arrows which you have over here. Now, so you see, it's a very interesting problem. So interesting problem in the sense that for the beam about the longitudinal axis, you have points within the beam. For example, see at the top over here, the shear stresses are 0. So you have the 0 shear stresses here. The complementary also about the longitudinal axis is 0. So here you just have the bending stresses, whereas at the neutral axis, the bending stresses disappear. You have 0 stresses at the neutral axis, 0 stresses, 0 strains. And at the neutral axis, you have the shear stresses which peaks up, right? So in between, if you take an element, for example, this element which I drew over here, that element has both the normal stresses as well as the shear stresses. So if I represent the stresses in this element will also have some amount of shear stresses for that matter over here. So it has both the shear stresses as well as the longitudinal stresses. Now again, remember these elements which we are looking at, see the sides of this element. The sides of this element are perpendicular to the longitudinal axis of the beam, and the top of the element are parallel to the longitudinal axis. So let's take maybe a cleaner version of this figure over here. So essentially this is what you have, right? So at the center of the beam at the neutral axis, this is the neutral axis which is passing through. You have the shear stresses which become, and again remember, so this is if I'm representing at the top the bending stresses maximum as sigma m. At the center, say the shear stresses are maximum, and let me call that shear stress the tau m over here. So at the neutral axis, you have the tau m's over here, and at the top you have the sigma m, and in this case, say just for this example, you have tensile over here and the compressive at the top. So these are again the directions, or the sides are either parallel or perpendicular to the longitudinal axis. Now take a look at this element over here. See this element that you see, it has only bending stresses, no shear stresses. So this element, that means that this element is already in the principal direction. Why? Because we know that for any element, a principal direction is the one in which you only have normal stresses and no shear stresses. So this one I have no shear stresses. Whereas you see an element over here, this element has both sigma x as well as the tau xy. So here at this location of the beam, there must be a rotated element, or in other words, a different plane where the taus disappear and the sigma increases, and sigma becomes the principal stresses over here. So something like this. If you take a look at all the different elements that you have, it is something like this. See, the top one stays the same because it is already in the principal directions, whereas the ones below over here, these are now rotated about the principal direction. So essentially the stresses you have are the principal stresses. So now the question is, can there be a point in the beam? See, for the regular bending case, we have seen that the maximum stresses happens at the top and the bottom over here. So can it happen within the beam? You have other locations where these stresses, after the element is oriented about its principal directions, can these stresses ever be higher than the maximum stresses which happen at the extreme fiber? So that is the question. So can the principal stresses sigma x be ever higher than the sigma m which you have at the top and the bottom? So we will solve an example problem through which you will find the answer to this question, and you will see for beams of different types of cross sections. This can happen, this cannot happen. It's an interesting problem. So let's do a problem example and find that out.